Hello everyone, I'm Luke, a PhD student at Oxford University. I hope you all are enjoying the workshop. Unfortunately, I'm not able to present live during the workshop, but I hope you enjoyed this recording of my presentation. Since this presentation is recorded, there will naturally not be a Q&A afterwards. However, I wanted to say at the beginning of this presentation that if you have any questions that you'd like to ask me, or if you'd just like to start a discussion about the paper, you're more than welcome to reach out to me via email or any other means of communication. With that being said, I'll dive into today's presentation. Today I'll be presenting intrinsic gradient compression for scalable and efficient federated learning, which is work done with my wonderful collaborator Franklin Wang from Harvard. Here we have an outline of today's presentation. I'll begin with an introduction and give some background about the problem that we're solving. Next, I'll provide some motivation for our work and discuss our method. Our method is composed of 3 algorithms for federated learning. We call these algorithms static intrinsic gradient compression, time-varying intrinsic gradient compression, and k-varying intrinsic gradient compression. Upon reviewing the methods, I'll dive into our experiments. We have experiments on 3 different tasks: image classification, language modeling, and text classification. I should mention up front that our paper is a general federated learning paper, but I suspect that given the NLP focus of this conference, you all will find the second 2 experiments, especially the second experiment on language modeling, to be hopefully quite interesting. Finally, I'll discuss some potential avenues for future work and conclude. Let's now discuss background and motivation. Of course, some of this will all be very familiar to you, given your experience with federated learning, but I feel that it's quite important to state it nonetheless. As you know, federated learning is a rapidly growing area of research which seeks to perform machine learning in an efficient and privacy-preserving way. It achieves this by training a model across multiple decentralized edge devices, which each hold their own local data samples. Crucially, although the edge devices send model updates to a central server, or to one another in the decentralized case, they do not send their private data. And for this reason, federated learning holds the promise of privacy-preserving distributed machine learning. However, as you guys know, federated learning with deep neural networks suffers from a problem with communication bandwidth. It's very costly to send gradients or model updates over a network, especially when communicating with mobile and edge devices. This problem is especially pronounced in 2022, as we're seeing bigger and bigger models become more commonplace throughout all of machine learning, especially natural language processing. Of course, this is not a new problem. This problem was identified by early research as one of the primary challenges to the real-world deployment of federated learning. And indeed, some of the earliest papers in federated learning proposed some simple methods for trying to deal with the problem of high communication bandwidth. And as you all are probably aware, there's a significant amount of research on reducing communication bandwidth by developing more sophisticated federated learning training strategies. These setups generally involve local computation with periodic communication, and then there is some form of model averaging involved, the simplest of which is Fed average. So these setups are very interesting areas of research, but we're working in a slightly different area. So we follow a line of research on reducing communication bandwidth via gradient compression. So these setups are very well suited to real-world settings because they don't involve any complex training setups. We simply propose to reduce the size of model updates by compression. And since these are gradient compression methods, they can be combined with other advancements in federated learning. So for example, our method can be combined with Fed average or Fed prox or whatever your favorite federated learning training strategy is. Now I'll dive into our method. So we begin by considering the root of the communication problem, which is that modern neural networks, such as BERT and GPT-2, are highly overparameterized. This statement is widely acknowledged throughout the machine learning community, and there's been a large amount of research in other subfields of machine learning relating to this idea of overparameterization. In particular, This paper is inspired by ideas from the machine learning theory community, which has spent a huge amount of energy trying to better understand why over-parameterized networks perform so well. And specifically, we're going to build off the idea of intrinsic dimensionality. This idea tries to answer the question, why do hugely over-parameterized models generalize so well, by asking, well, how much of our parameter space is really necessary for successful optimization? More formally, the intrinsic dimension of a given optimization problem is defined as the smallest dimension, d, for which we can solve the problem when the weights are restricted to a d-dimensional manifold. So precisely, it's the smallest d for which the standard learning problem has a satisfactory solution where the parameters are constrained to a d-dimensional manifold. If the intrinsic dimensionality of a problem is low, then only a small number of parameters are needed to obtain a good solution. So for example, consider text classification with an RNN that has 1 million parameters, and we consider satisfactory performance to be 90%. The full parameter space of our model is of course 1 million dimensional, so we say that the extrinsic dimension of the problem is 1 million. However, if, say, we can optimize in a 100-dimensional subspace of this 1 million dimensional space and still obtain satisfactory 90% accuracy, then we say that the intrinsic dimension of the problem is at most 100. And of course, I haven't described yet how to optimize in this 100-dimensional space, but that will be explained later. So if the intrinsic dimension of a problem is low, then even if the model is vastly over-parameterized, only a small number of parameters are needed to solve the optimization problem. And this is the difference between how many parameters a model has, the extrinsic dimensionality, and how many parameters the model really needs, the intrinsic dimensionality. So based on this, you could ask, how large is the intrinsic dimensionality of common NLP problems? And the answer, as found by some recent work, is actually very low. So this leads us naturally to think that this idea could be highly useful in a federated setting. Specifically, if the intrinsic dimension of a problem is low, then we can formulate a corresponding low bandwidth learning algorithm by running stochastic gradient descent in the intrinsic space rather than in the extrinsic space. And if the intrinsic space is much smaller than the extrinsic space, then this could massively save on communication bandwidth. So how do we actually implement the idea of intrinsic dimensionality? Well, the naive way would be to just train a subset of small d parameters, right? So this subset of small d parameters is a small d dimensional subspace of the full big D dimensional parameter space. However, this is clearly not a satisfying solution, and indeed it doesn't work very well in practice. So instead, we optimize in a random d-dimensional subspace of the full big D dimensional parameter space. And we do this by projecting our weights into a small dimensional space with a random matrix A. So this random matrix A is the size of the full space by the size of the intrinsic space. And this is what is going to effectively compress our model weights. So here, once we have formulated the problem in this way, then gradient descent is simply given by the normal formulation with an additional A factor, so an AA transpose factor. And here we can see that this corresponds to a compressed gradient where you multiply the gradient by A transpose, and then an approximate uncompressed gradient when you multiply by A again. And we refer to this method as static intrinsic gradient compression because A is fixed. And later we're going to extend this to slightly more complex setups. The previous formulation of SGD corresponds, as we said, to a federated learning algorithm, which we're going to call static intrinsic gradient compression. And here we use little d bandwidth for both upload and download. However, as we've mentioned, this has a couple constraints. So A in this formulation is the same for the entire duration of training, and it's the same for all clients. In our second algorithm, which we call time-varying intrinsic gradient compression, we relax the constraint that A is fixed across time. So gradient descent is now given by this new equation, where the A is indexed by the epoch E. So this is, compared to the static version, this has the advantage of exploring more of the parameter space over the course of training. And as we've seen before, this gradient compression corresponds to a federated learning algorithm. This takes D upload bandwidth and 2D download bandwidth per epoch because we change at each epoch. Finally, we have K varying intrinsic gradient compression, which further relaxes the constraint that A is the same across all clients. So instead, we use a total of K matrices, A sub E to the K, not multiplied K times, but just indexed by K. And gradient descent is now given by this updated formula, which you've seen here. This again corresponds to a federated learning algorithm, which takes little d upload bandwidth and K times little d download bandwidth. So here we have a comparison between the approaches. We can see that static and time varying compression are well suited for cases where upload and download are similarly costly, whereas K varying compression is very well suited for cases where upload is very costly and download is not very costly. This is often the case, for example, with edge devices, where they're often able to download, but upload might be quite costly. So the last thing we have to describe is the choice of our matrix A. Forming and communicating a dense random matrix is prohibitively costly, both because you cannot send A, and also because if we were to train, say, a 100 million parameter model with an intrinsic dimension of 1,000, we would need to store an enormous matrix. So instead, we note that we don't actually need A. We only need the matrix vector products, AX and A transpose Y, and so we use a fast food transform to express A as a matrix product. We're then able to use the fast Walsh-Hadamard transform to compute very fast matrix vector products, and the fast Walsh-Hadamard transform is a variant of the very popular fast Fourier transform, so it can be computed in n log n time, which is more than fast enough for our setting. Now I will describe some experiments. We conducted experiments on 3 different tasks, so these are all federated learning experiments with a simulated setup, because we do not have thousands of devices. The first of these is image classification with CFAR10. The second is language modeling on the persona chat dataset. And the final experiment is on text classification with the Stanford Sentiment Tree Bank. For CFAR10, we use the same setup as SketchSGD. So this is a non-IID data split between 10,000 clients in which each client only has data from a single class. At each step, we sample 100 clients, and then we measure accuracy. We look at intrinsic dimensions from 4,000 to 256,000, and we perform experiments with static and time-varying gradient compression. So here you see some results. Higher corresponds to better accuracy, and further to the right corresponds to greater compression. So you can see that the uncompressed model has very high accuracy, and these are our models, so static and time varying respectively. And you can see that we have a very strong trade-off between compression and accuracy. And these different dots correspond to different intrinsic dimensionalities. So here we have intrinsic dimensionality 256,000, which provides relatively low compression, 4x compression, while here we have intrinsic dimension 4,000, which provides very high compression with lower accuracy. Here we have a comparison over time. So this is just training curves of uncompressed, static, and time-varying compression. And what we can see here is that as the number of iterations increases, the time-varying model approaches the performance of the uncompressed model because it explores more of the parameter space over time, whereas static somewhat plateaus because the static version is restricted to a fixed low-dimensional subspace. Next, we perform experiments on language modeling on the persona chat dataset. So this uses the GPT-2 model, which has 110 million parameters, and here we're doing federated fine-tuning. The data has a non-IID split into 17,000 clients, and it involves 2 rounds of training across all clients. We experiment with these algorithms with intrinsic dimensions from 16,000 to 4 million, and again, we compare to a number of previous methods. Here, we're looking at perplexity, so lower is better. Here you can see the uncompressed, and then again, our methods provide a good trade-off between compression and perplexity. Finally, we conduct experiments on SST2, so a standard text classification benchmark within the GLUE set of benchmarks. This data setup is simple, and the purpose of this experiment is simply to push the limits of intrinsic gradient compression. So here we can see time varying and static intrinsic gradient compression, and this line at the top is uncompressed BERT. And essentially what we can see here, the two takeaways: one, time varying is slightly better than static for high compression rates, and most importantly, we're able to obtain very high compression rates with a relatively low drop in accuracy. So finally, I will conclude with some future work. So all of the experiments here have simulated federated learning setups, and naturally in future work, we hope to deploy our system in a real-world setting with a large number of physical devices. Then on the more theoretical side, it would be interesting to gain a better understanding of the intrinsic parameter space. Thank you very much. I hope you've enjoyed the presentation, and once again, please reach out to us with any questions or if you'd simply like to chat about the paper. Have a wonderful remainder of the workshop.